Welcome to lecture 70 on essentials of topology. In this lecture, we will study the formal proof of Tychonoff theorem. Begin with, let us prove a lemma first, which is based on the concept of Jones lemma, and this will be useful to prove the Tychonoff theorem. The lemma is stated as if we are having a non-empty set X and let us take this F, this be a collection of subsets of X with this collection satisfies finite intersection property, then there is a maximal family of subsets of X that contains F and also it has the finite intersection property. From the statement itself, it is clear that we are going to use Jones lemma in between. So, how to use this concept? Let us see it. So, what we are doing that we are beginning with a collection. Let us denote this by A. So, let A be the collection of all, this is families of subsets of X, and these satisfy, that is which contain the given family F, and also these have Fi, and on this set we are going to define a relation. So if we are defining a binary relation, so let us define a binary relation, and this is less than or equal to this in on A. And how this relation is defined, that if we are taking two elements F1 and F2, these from this family, that is A, we say that F1 is related to this F2 provided this F1 is contained in F2. It is trivial to see from here that this relation, that is less than or equal to, this is a partial order on this A. Now what we can do, that we can justify that this set A, this has a maximal element. Question is how to justify it. Answer is, why not let us use Jones lemma here. But if we are going to use the concept of Jones lemma, let us take any linearly ordered subset and try to justify that every such subset has upper bound. So what we are going to justify, that every linearly ordered subset of this A has an upper bound. So what we are taking here, let us take this set, this is D, this is a linearly ordered subset of A, and what we can justify that it has an upper bound. Note that this is arbitrary one, so we have taken this T as arbitrary. Now in order to justify this has an upper bound, let us take union of all elements of this linearly ordered subset and denote this by C. Question is, can we justify that this is an upper bound of this T Answer is yes, and for which what we need to justify. Actually, we have to justify 2 points. The first one is that this union, that is this C, this contains this family F, and the second one that C has the finite intersection property. Question is how to justify that this C contains S. Answer is it is to be noted that this D is an element of this linearly ordered subset, and it is to be noted that every D is containing F, and if every D is containing F and as C is union of all such D's, we conclude that this C always contains F. Now, if we want to justify that this C has finite intersection property, what to do? Let us take some or any arbitrary family C1, C2 and Cn from this collection C. Now what we can do that because C is nothing but union of such D, so we can make a guarantee that for all I which is greater than or equal to 1 and less than n, there exists some Di in this collection such that what we can conclude? We can conclude that this Ci belongs to some Di where I lies between 1 to n. But at the same time, there is an special feature with this D, that is because this D is linearly ordered. So what will happen? There exists an element dk in this D which will contain all such di, and if this is containing all such di, what we can conclude that this C1, C2 up to Cn, these are member of this dk, and if these are members of dk, it is to be noted that this dk has finite intersection property, that is FIP. Therefore, we can conclude that C1 intersection C2 intersection up to Cn is non-empty. Therefore, from here we can conclude that this C is an element of this family what we have taken here, that is A, and this is an upper bound of this linearly ordered subset of A. Thus, each and every linearly ordered subset of A has an upper bound, and therefore we can use Jones lemma here. So by using this Jones lemma, what we can conclude that this A has a maximal element. Having this idea in the mind, now we are ready to prove this Tychonoff theorem. So we have already seen what the statement of this theorem is, that is an arbitrary product of compact topological spaces is compact in the product topology. Let us try to prove it. In order to prove it, why not? Let us begin with an arbitrary family, that is, this is an arbitrary family of topological spaces. So we are having this family of topological spaces. This is given to us that this is a family of compact topological spaces. So this is given to us. Now let us assume that the product of these xi, I belongs to I, we are taking this as x. So what we have to justify that this x with product topology on it, this is compact. In order to justify that this space is compact, we are going to use the characterization of compactness in terms of finite intersection property. A glimpse we have already seen in the previous lecture that how to use that property here. So idea is if we are taking a family F and what this family is, let us take that this is any family of closed subsets of this product space and this is having finite intersection property. So in order to show that this is compact, we have to show that this intersection of F, F is coming from this family which is having a phi p. This intersection is non-empty. So we have to justify it. Now by using the previous lemma, what we can conclude here that there exists a maximal family. Let us denote that maximal family by this M of this is subsets. But note that these subsets are not necessarily closed. And these are subsets of X that contains this F and they are or it has FIP. Now if this is the case and because this family M is the maximal one, from the maximality of M, what we can conclude that this intersection of such F is from this given family or which we have assumed, this will always be superset of intersection of M. M is coming from this family that is the maximal one. Now if we are taking the closure of both sides, what we can say that this is intersection of this M where M is this maximal family. This will always be subset of this intersection of F where F belongs to this family from where we have started and we have to take its closure. But note that this is arbitrary intersection of closed sets. So it will be closed and therefore this is precisely the intersection of F where F is a member of this given family. At the same time, it is to be noted that this will always be superset of intersection of this M belong to this maximal family and closure of M. From here, what we have with us that the intersection of closure of M where M belongs to this maximal family, this is a subset of intersection of this F where F is from the given family of closed subsets of X. Now, if we can show that this set is non-empty, then obviously this will be non-empty and therefore we can conclude the result. So finally what is our motive or what we want to justify that we want to justify that intersection of this closure of M, where M belongs to this maximal family, is non-empty. So this is only the result which we have to deduce to prove this theorem, for which we have to show that there exists at least one element in this intersection. So, in order to find out that element, and before making some final constructions, we are going to deduce two results, and by using these two we can construct that element. So what exactly we are going to do is that first, what we are making a claim that if we are taking a finite number of members in this maximal family, what will happen, their intersection, that is M1 intersection M2 intersection, let us take that this is Mn, this Mn will always be an element of M. So how to justify it? What we are assuming that, let us take that this intersection is M. So M1 intersection M2 intersection Mn. We are taking this as M. Now, if this M is not an element of this maximal family, what we can do that, if we are taking this maximal family along with this M, let us take this set or this collection as M dash. It is to be noted that this M is properly contained in M dash. So what feature this M dash has? So the first one is that this M dash contains F. Question is whether M dash has FIP. Let us discuss it. We can show that this M dash has FIP. How to justify it? Why not let us take some elements, that is M1 dash, M2 dash, and let us take this is MP dash. These are elements of M dash. Now what will happen if, for example, none of these, what we are taking Mi dash, are equal to this M what we have taken here, that is intersection of these, then what will happen, actually this M1 dash, M2 dash and MP dash, they will be members of M itself, and therefore this M1 dash intersection M2 dash intersection MP dash will always be non-empty. Now if any of these are equal to M, what will happen? Note that M itself is nothing but M1 intersection M2 intersection this Mn. So note that M1, M2 and Mn, all these are members of M and they are finite in number, and as M has FIP, so in this case too, if any of these Mi1 dash or M1 dash, M2 dash and MP dash are equal to M, obviously their intersection will always be non-empty. That is, if we are taking something like M1 dash intersection M2 dash intersection, and this is some of the element, that is M intersection this MP dash, obviously this will be non-empty. And if this is non-empty, what we can conclude, the M dash which we have taken here, that is containing F, and at the same time this is having FIP. but at the same time it is to be noted that this m is maximal. And now if m is maximal, by maximality of m we conclude that m is equal to m dash, which is a contradiction because as per our construction m is properly contained in m dash. And why this problem arises? Because we have assumed that this m is not the member of this maximal family, and therefore we conclude that this m is a member of this maximal family m, or what m is precisely, that is m1 intersection m2 intersection mn is always an element of m if m1 m2 mn all are members of this m. Now let us make a second claim. What is it? This is precisely if we are taking a subset n of x. Now, what property this n has? Actually, this n intercepts non-trivially every member of m. If n has this feature, what we can claim that such n will always be a member of this maximal family. Question is how to justify it. Similar to the previous one, what will happen if this n is not member of this maximal family? So what we can do that, let us construct another family, and which is nothing but which is obtained by adjoining this n to this maximal family. Let us take that this family is m double dash. Now from this construction, this is clear that this m is properly contained in this m double dash. Now again, what are the features of this m double dash? First thing is that m double dash this contains this f, and question is whether m double dash has FIP. Let us try to justify it that this m dash has FIP. Question is how to justify. So let us take some members, that is this m1 double dash, this m2 double dash, and let us take mk double dash in this constructed family, that is m double dash. Now there will be two cases. The first one is that if all these are, that is m1 double dash, m2 double dash, and this mk double dash are members of this m itself, that is none of these are equal to this n which we have taken, then obviously from here what we can deduce that this m1 double dash intersection m2 double dash intersection mk double dash is non-empty, and this is because this m has FIP. Also, if any of these are equal to n, what will happen? Even if we are taking n intersection all of these, let us take m1 double dash intersection m2 double dash intersection mk double dash, and if we are replacing one of the element by n itself, then this will always be non-empty. Why? Because of our assumption that n intersects non-trivially every member of m. Therefore, what we can conclude that this m double dash this has FIP. Plus we have already seen that this contains F. Now Also, it is to be noted that this m is properly contained in m double dash, but at the same time, this m is maximal. So, we again reach to a contradiction because no superset of it can have a phi p and contains F because of its maximality, and therefore we conclude that this n will always be a member of this maximal family. So with these two concepts, let us try to find an element, and that element should be member of this particular intersection. Question is how to construct this one. So we are going to take the help of projection maps. So what we can do that for each I in I, let us take the projection map pi I from this product space, that is X with product topology, to the topological space xi tau I. Now, what we have already seen that the family which we have chosen, that is this M, that was a maximal family. This is collection of subsets of Ex, and at the same time this contains F, and this also has FIP. Now, by using this projection map, let us choose a family of subsets of xi. So this is pi I m, where m is a member of this maximal family. It is to be noted that this family has FIP. This is a collection of subsets of X, but question is whether each pi im is closed. Answer is not necessarily. So what to do? Why not let us take a family of subsets of X that is given by closure of these pi im, where em belongs to this maximal family. Now, what about this family? We can say that this is obviously closed subset of xi, and at the same time this family has FIP. So this family is actually the family of closed subsets of xi. Now, what information we have with this topological space? It is to be noted that this xi tau I, this is compact. So let us use the compactness of this space. We can conclude that if we are taking intersection of these pi im closure, where em belongs to this maximal family, this will always be non-empty. So what we can do that if this intersection is non-empty for each I, that is thus for each I in I, what we can choose, we can find an element xi in this intersection. So this is intersection of this closure of pi im, where em belongs to this maximal family. And now by using this xi, what we have already studied in the previous lecture regarding the construction of an element in the intersection, let us construct an element x, which is constructed by using these xi's, where I belongs to I. It is clear that this x is an element of x, that is precisely the product of xi's I in I. Question is whether this X is an element of intersection of closure of M, where M is a member of this maximal family. Answer is yes, and B can justify it. How to justify it? For its justification, let us take an open subset of X. So what we are taking, let us take this GB or tau P open subset of X, that is, this is open set in product space, and at the same time, why not let us take an element of this G, let us take this X in G. So what we can conclude that, why not let us use the concept of basis. So we can talk about a basic open set. So there exists a basic open set, and let us take that basic open set in the form, that is intersection of these pi I inverse gi, where I belongs to j, such that what we can conclude that X is an element of this I belongs to j. Let us take this intersection, this pi I inverse gi, and this will be a subset of G. It is to be noted here that this Gi is an element of tau I. Also, what about Xi? This will be an element of Gi. Finally, this J, which is a subset of I, this is finite. Question is, why we are choosing this basic open set in this particular form? Answer is that because Gi is a member of tau I, collection of such elements form a subbasis for product topology, and if we are taking their finite intersection, that will be a member of basis for product topology. Now, what we can conclude from here, it is to be noted that this Xi belongs to Gi, and what we have already studied, that Xi is an element of this intersection. So this Xi is an element of this closure of pi im, and it is to be noted that m is an element of m. So what we can conclude from here by using the definition of closure, that this Gi intersection, this image of M under this projection map, this will always be non-empty, and this is true for all M in this maximal family. Now, if we are computing, or from here, what we can conclude that this pi I inverse Gi intersection M will also be non-empty, and this is true for all M in M. And from here, what we can make a guarantee from the result which we have discussed, this pi I inverse Gi is an element of this maximal family for all I in this J. It is to be noted that this M has FIP. Therefore, finite intersection of such members will always be non-empty. Thus, what we can conclude that if we are taking the intersection of these pi I inverse Gi intersection over I in J, let us take this intersection with any M, that will always be non-empty. This is true for all M in this maximal family. Now, it is to be noted that what this set is. This set is contained in G, so we can conclude from here that this G intersection M is non-empty, and this is true for all M in M. What G is an arbitrary open subset of X. So from here, what we can conclude that this X is an element of closure of M, but note that that is true for every M in M. So we can conclude that X is an element of intersection of this closure where M is an element of M. Thus, what we have shown that this intersection of closure of M where M belongs to this family, this is non-empty. Also, if you recall what we have shown or what we have deduced, that this intersection of M closure where M is a member of this is a subset of intersection of F. F belongs to the family of closed subsets of X having FIP, as we have shown that this is non-empty. Therefore, the conclusion that is F belongs to this family, and let us take their intersection. This intersection is non-empty, and hence this product space X tau p, that is with X with product topology, this is compact. So this is the proof of Tychonoff theorem. These are the references. That's all from this lecture. Thank you.